All right, this video is to go over the notes for probability distributions and to explain and how to use a probability distribution. But first, we want to review some basic probability. So our warm-up reads, in a bag of donut holes, there are 12 glazed, 10 chocolate, 8 blueberry, and 15 jelly filled. Select one donut hole at random. Find the following probabilities. Well, hopefully you remember that to find a set of probabilities or to solve probability problems, we need to know how many things we're choosing from. So in this case, we add up all the different numbers that they give us. So the 12 glaze, the 10 chocolate, the 8 blueberry, and 15 jelly filled, and we find out there's a total of 45 donut holes, right? A total of 45 donut holes. That's important. Because when I solve probability problems, what I'm always looking at is the number of outcomes that satisfy the condition, in this case, chocolate donut holes. That would be 10 divided by how many I have. And so 10 over 45. Well, those are both divisible by 5, so that's giving me 2/9. So I could express my probability as a fraction, 2/9. I could express it as a decimal to 4 decimal places, what I usually use. Or I could express it as a percentage, 22.22%. And all of those would be acceptable. But again, the basis for it is I take the number of outcomes that meet the condition divided by the total number of possible outcomes. So for glazed or blueberry, I'm looking at how many donut holes that I have that are glazed and how many are blueberry. It turns out there's 20 in total because I've got the 12 plus the 8. Again, 20 and 45 are both divisible by 5, so I'd have 4 over 9, which again could be expressed as 0.444 or even as 44.44%. Now, not jelly-filled takes a little bit more thinking because they tell me that I have 15 jelly-filled donut holes. So for the ones that are not jelly-filled, I have to think, well, 45 minus 15, that's 30, and so I'm going to be doing 30 out of 45. All right. And both of these are divisible by 15, not just by 5. And that gives us 2/3. So that's one way to express the probability. If I was going to do it as a decimal, I would do 3 sixes rather, and then a 7. So I want to use rounding there if I'm going to go to 4 decimal places. And if I was going to do this as a percentage, I would say 66.67%. And then coming to part D, again, a little bit of thinking. I don't want chocolate or glazed donut holes. So the one that I'm drawing at random, I do not want it to be chocolate or glazed. So they tell us there's 10 chocolate and 12 glazed. So that gives us 22 that we don't want to select. So 45 minus 22 gives us 23 that meet that condition. And so 23 over 45, well, that's actually in simplest terms. And as a decimal, that would be 0.511. Or I could express it as 51.11%. So again, when we talk about probability, what we're looking at is the number of outcomes that meet our condition divided by the total number of possible outcomes. So in class, we did an activity for how many siblings do you have? And we constructed what's called a frequency distribution. All right, or a frequency table. And I just polled the students and said, how many do you have? And then we examined that and we turned it into a probability distribution. And we established that probability distributions, to be a valid one, have to have 2 possible scenarios. And so we're going to define those when we get down here to the vocab. Then we practice it again, working on some data with 25 bags of M&Ms. We didn't actually open bags of M&Ms in class for activity. It gave us data. So that way we're all working with the same data. So let's go to the vocabulary. So remember that set of all possible outcomes I was talking about? That is what we call our sample space. So a sample space is the set of all possible outcomes. Okay. And so in class, if you go through the notes for class, that would be the number of, let's see, for the opening warm-up, it would be the total number of donut holes. Okay, so I can say the total, or the total number of donut holes. For the siblings, it would be the number of students in the class. And I think for first block, it was 20. number of students in the class. And for the M&M activity, our sample space would be all 25 bags of M&Ms is what they used in the activity. They gave us data on opening 25 fun-sized bags of M&Ms. So it's the set of all possible outcomes. So in that one, we were selecting one bag at random. We were calculating the probability of how many M&Ms would be in the bag. A probability distribution then is simply a table that displays all of the possible outcomes for a random variable. Remember, all a random variable is any variable that could have a series of different outcomes and their corresponding probabilities. So the table would basically have two rows or two columns. I've seen them expressed in a vertical form. Usually they're horizontal though. It would tell me all of the outcomes, like number of candies in the bag, right? And so I'd be looking at all 25 bags. What were the possible candies in the bag? And then below that, I would give you the probability based on the data that we had. Now, we have probability distributions, and the ones we're looking at in this unit it starts with discrete random variables, and then it goes to continuous random variables. So let's talk about what those are. So remember, a discrete random variable is just a random variable whose outcomes, when plotted on a number line, have space between them. So in other words, if I were to plot the outcomes for the number of siblings on a number line, I'd have 0, 1, 2, 3, 4. And in first block, we got all the way up to 8. We had one student that had 8 siblings. But between 0 and 1, there are numbers there that are not outcomes for that random variable. Between 1 and 2, there are numbers between 1 and 2, like 1.5, 1.75, 1.8, 1.1, that are not outcomes for that random variable, because the random variable is representing the number of siblings. So that makes that random variable, the number of siblings, be a discrete random variable. On the other side of that, though, we have what are called continuous random variables. And these are random variables, so a random variable whose outcomes, when plotted on a number line, do not have space between them and must be represented using an interval. Okay. So when I look at the outcomes for a continuous random variable, they don't have space in between them, because it could be any rational or irrational number along the number line. So if I was looking at birth weights of infants born at, say, Rex Hospital in December, this would be continuous because it depends on the accuracy of the scale, but really it could be any number in there. It's not a fixed number of outcomes, right? Like siblings. So we have to do it over an interval. There are probability distributions, but the first few lessons are going to focus on discrete random variables, and then we'll get into continuous random variables, something like the normal distribution. So let's take a look at an example of the kind of things you could be asked, all right? A family has 3 children. Oh, I forgot to talk about the conditions. Let me put the conditions up here for a probability distribution. Those are important because we're about to ask a question about it. So let's go back up here. And so a probability distribution has 2 conditions to be valid. Number 1, the probabilities have to, probabilities, there we go, have to be between 0 and 1 inclusive, meaning they could be 0 or 1 themselves, all right? For instance, when we did the how many siblings do you have, we had some sibling counts that there were no students that had that number of siblings, so the probability of that was 0. Also, the probabilities probabilities, I was about to misspell it again, have to add up to 1. Okay? Because the idea is we're accounting for every possible outcome. So when I look at their corresponding probabilities, they all have to add up to be 1. So if a probability distribution meets those two conditions, then it's considered to be a valid probability distribution. All right? And don't ever assume that those conditions are met. You always want to make sure that they have been met. So a family has 3 children. Let X represent the children who are boys. So this is the number of boys they have. Below is a discrete probability distribution for X. Now, for this random variable, we're assuming gender is 50-50. We know that genetically that's not always the case for couples, but that's what we're using for this probability distribution. So check that the table above is a valid discrete probability distribution. So our first condition, probabilities are between 0 and 1 inclusive. And I look at all my probabilities, and I see that they are. There is nothing less than 0 and nothing greater than 1. So what I do is say, yep, I've checked that condition. Our second condition then is that they all add up to 1. So probabilities add to 1. And so what I would want to do here is take a calculator. So for instance, I'm going to grab my calculator here, pull it off to the side. And I'm going to say, let's see, the probability that they have no boys is 0.125 plus the probability that they have exactly 1 boy and their 3 children is 0.375. And the probability that they have 2 boys is exactly the same, 0.375. And then the probability that all 3 children are boys is 0.125 again. So I'm going to check, and sure enough, they all add up to be 1. So because both of those conditions are met, this is a valid probability distribution. And I can use it for answering questions like here in this next question, okay, in number 2. So it says, what is probability X is greater than or equal to? And remember, X here is signifying how many boys the couple has in their 3 children. Express this probably both numerically and in words. Okay, so let's talk about this. So here it says the probability that X is greater than or equal to, let me get that symbol in there, greater than or equal to 2. And so what that means is basically, if I were to convert this into words, we'd be talking about the probability is at least 2 boys. And so really that means 2 or more. So in this case, since they're having 3 children, that would be that they have 2 boys or 3 boys. And so what I would do is I would say the probability of having 2 boys, let's see here, 2 boys, plus the probability of having 3 boys. So 3 boys. And so that's really all I'm doing is, since I said at least 2, it's really 2 or more. And the only conditions that meet that are 2 and 3 in this table. So then I'd pull out the probability 0.375 for 2 boys plus the probability of 0.125 for 3 boys, and that equals 0.5. So to express this in words, I kind of did there in that second statement, but what I would say is the probability that the family, or the couple rather, the couple has at least 2 boys among, let's just say 2 boys. I was going to say among their 3 children, but just say the probability that they have at least 2 boys, okay? You could say 2 or more boys, at least 2 boys. And this is different than saying more than 2 boys, all right? More than 2 boys, the only condition that would meet that would be 3.